Yeah, welcome back to our statistics course. Today we want to start a regression by our own, but not only by feeding in the data within the software, clicking enter and getting the output. This is of course also possible, but I really think doing it, so to speak, within a software package by hand, then hopefully you will learn what linear regression is about. Last time we started with this example that in general, quite often in economics, we have some data and then we have an idea that somehow these variables, profit, costs, number of employees, budget of marketing, how many stores do I have, how much I'm investing in my web presence and so on, that all these variables are sticking somehow together. And then the first starting point quite often is that I somehow want just to calculate in a quantitative way the dependence between these variables. What happens if I'm investing more in my web presence? What does this have for an impact the last 10 years on my revenue, for example, or on my costs, or whatever? And here we had this example that we said, well, we have some company, and in a classical way, you can think of your employees. They are starting and going from door to door and asking, do you want to buy my washing machine or something like this? And how many visits, what kind of impact does this have for the sales volume? And of course, in general, we would think that, where is it here, that hopefully the number of visits and your sales volume has a positive dependence, which we can see in this diagram within our data. Well, and then, we just can think in our company, well, if I have in general this positive dependence, if I hire a new person, and maybe then I can double the visits, what kind of impact this would then have on my revenue? Do I, from my former data, is it then possible that I can double also my revenue, or even more than doubling it? And this I want to get out of my data, and for this we then want to fit, where do I have it here? Just a good linear line within these data points. And last time, then I gave you this huge theoretical calculation, because what we then want to do is, of course, every data point has some distance to our regression line. Maybe there are some data points lying just on this line, but in general, I will have a distance between a fitted line and my actual data. And then I recommend, or I introduced that our aim is then to minimize the squared distance, the sum of all squared distances of the data points with respect to, at that stadium, not known regression line. Because from this minimization process, then we obtain the vertical axis cut and the slope of our regression lines. Well, and then I also explain to you why we are using these square distance, why not the forced distance, why not only the absolute value. And one practical issue, taking the square just means that if I'm above or below my regression line, then the distances are calculated in the same way, that they didn't cancel out. And the second one is that it is very highly related to our normal distribution. And quite often, if we don't know how our errors, these epsilons, are distributed, then quite often we make the assumption that they are normally distributed. Well, and this is motivated by the central limit theorem. And hopefully you have talked about the central limit theorem of statistics in your introductory courses, that if I increase my data set from 100 data points to 1,000 to 10,000 and so on, that then the average of my data points will be in the limit normally distributed. And this can be theoretically shown. Although I don't know the actual distribution of my data points, just if my sample number is high enough, then I know that the average of my sample is normally distributed. And this is, a very, very powerful theoretical result. Well, and the normal distribution, there I know this is exponential to x minus expectation value in brackets squared. So there I have also this squared distance in describing the normal distribution. And the last point was one of you has the topic in the term paper, maximum likelihood estimation. And there it can then also be shown that the maximum likelihood estimator is the best estimator for squared distances. So maybe this comes then also out of this term paper. We will see this then. Okay. Well, and if I do all these minimization, then I have just a function depending on two parameters. And minimizing this function then means just taking the derivative with respect to these two parameters. And then, I have to know somehow how to deal with all these summation signs. And in the end, I obtain then these formulas for our regression. Well, and they look quite complicated. But if I look in a deeper way, just what do I have here? This is just the summation over the product of x and y. So x times y is again only just a number. This is xy, 1y, plus x2, y2, plus x3, y3. So I'm again just adding up n numbers. And adding up n numbers is just n times the average. Because the average, arithmetic mean, is just defined, summing up all my data points dividing by n. So what then I obtain here is that this number is nothing else than the average of the product of x and y. But there you have to keep in mind, at first you have to take the product and then averaging. Oh, this is wrong here. I see. Sorry, this I have to change, because here I have the average only of x, so this has to be x times y. And if I look in the denominator, then again, this is nothing times else since xi times xi. So this is again only just a number, x1 squared plus x2 squared plus x3 squared. And so again, this is only the average of the xi squared. So here then the averaging process is also above the exponent 2, and here the square is outside the summation, so I'm at first averaging x and then squaring, and therefore it is written first the average over x and then the squared on this position. And if we look at this formula, then you can write it also as xy bar minus x bar y bar over x bar times x bar minus x times x bar, and the other one x bar times x bar. So in order to keep this in mind, this is both more or less the same, just in the denominator you exchanging x and y. So here and here. Okay, and then later on we will come to the what we are meaning by covariance is that B can be also written like this. This we will show in an exercise. Yeah, and now, as I told you, we want to calculate the linear regression just with our example. Therefore, I copy the data and going to Excel. So you see all this? Yeah, and then let's have a look within our formulas. What do I need? I need the sum of x, here for B, the sum of x and y. I need the sum of x squared, and I need always the sum of x and the sum of y. Nothing more. And for this, I already wrote down here x times y and x squared, and down here we can just write sum, and then we are summing up all numbers of the x, so equals sum. This is 70 summing up all y's. Then we need 9 times 24, 11 times 33, and so on. This we can copy going downward. Then we not need x times x, so 9 squared, 11 squared, and so on. Copying downward and taking always the sums. Well, and then we remember our slope b equals n. So at first we need also n for this. Let's take here another one. So how many data points do we have? Of course, we see that it is 6, but you can also have a time series with much more data. So let's just count this. So this is then n. So for B, we now know the average of x times y and times n. So equals 6 times the sum of xy 2134 minus sum of x, sum of y. Sum of x is 70 times 162 divided by n times x squared minus sum of x squared. So divided by 6 times sum of x squared, my 940, minus sum of x and outside brackets, so 70 squared. And if I now press enter, then I got a really wrong result, because y, of course, then only this part of my formula would be divided, and therefore I have to introduce the brackets within the formula. And then I have my value b. Well, and for a, I could use this formula here, or I use the result that I also know that the average of my data points, so xy and x bar and y bar, are also have to lie on my regression line. This was this center of mass theorem. And since I know that y bar is also equal a plus bx bar, this then I can solve for a, and then I can just directly calculate. This is a little bit faster than using also this formula. But anyhow, you can do it as you want. So this is then y bar, so 162. This is the sum of all y's. This I have to divide it by n, the amount of my sample, minus b, this I have already calculated, times x bar, and this is 70 divided by 6. And then I'm ready, and this we can of course also calculate with the direct formulas. A is our cut of the vertical axis, so the formula in German is Achsenabschnitt. Then you already see down here using the y numbers and the x numbers. So all y data and all x data. So this was A, sorry. And B is a slope. So in German, the formula is Steigung, and also the y data and the x data. And the third possibility, you have to obtain this is just taking your diagram, then, oh, this is why, because I also took the years. I also only want to take x and y. So I produce here just a diagram. then I always don't know which is which. Therefore, I just look it up. So C is X and D is Y. This is okay. And if you have this diagram, you can just click in the data, then right click with your mouse. Then you obtain this menu, and then you have here trend line. Putting trend line, this you don't see. And then you have here to use the option linear. And we want also to know what are the numbers, and here you have the option to get out the formula. And what is surprise? 1.9 plus 3.9 you have here too. So let's save this. Okay. So then we can put in all these numbers here. Hopefully this works. No, this doesn't work. Why not? I thought this is possible. So it is possible. Okay, then let's take also the sums down here. Somehow this, and that you can remember this, that B was then 6 times minus x bar, sum x, sum y, over 6 times x squared is 940 minus sum x squared. This was roughly 3.91, I think, or 92. And A was then y bar, so 162 over 6 minus 3.92 times x bar is 70 over 6, and this was approximately 1.98. Okay, and now we want to extrapolate this for x is 30. What do I have to do then? So now I want to make somehow my forecast. Until now, we see my maximum number of visits was 20. And with this regression, I can make now a forecast what would be my sales volume when I make 30 visits. What do I have to do then? Idea in the internet? Because this is why I'm doing this. I'm analyzing my data in my company, and then I want to have a hint, what should I do tomorrow? Or I want to have an idea, if I do something, what I'm expecting, what then happens. Well, I do not have to fill in here this table for this in order to answer this. This filling in this table I will do only in order to be complete, and we need this also afterwards when we are talking about correlations. So what do I expect if A is 1.98, I think, if I remember it right, and this was 3.98. Is it too early on Monday? So then I will increase the horizontal line going to, let's say, 40. And then we have also to increase this. Let's take 100. Let's make this a little bit smaller. 20. Take this up here. So, graphically, I just want to find this point here. And I'm interested here in the sales volume. So this is X and this is Y. My regression just was y hat equals A plus B X. Yep. Of course. So y hat of 30 is then of course, nothing else we are interested in. So let's do it also here. So y hat of 30 is then A plus B times 30 is 63.27. Oh, sorry, I changed the numbers. Oops. This was the other way around, sorry. So this is 1.98 and 3.92. So 3.92, 1.98, and then 63.27. So this would be 63.27. Yeah, and well, in order to be complete, then we can also calculate all, so to speak, theoretical values which correspond to an x of 9, an x of 11, and so on. So the numbers which are lying on our fitted line. And this, in order to be complete, we can add here y hat would be then a. When we want to copy down this formula, we have to fix this number. This is done by F4, and F4 just introduces for you these dollar signs in front of the C and in front of the 14, and this means if you are copying this formula, then this cell is fixed. And also what you can do is to leave out the dollar sign in front of the C, and if you then copy to the right, then the C moves to D, E, F, and so on. And this is also quite often comfortable, because sometimes you want to move when you are copying the letter, or if you leave out the dollar sign in front of the 14 and then you are copying downward your formula, then this will also shift from 14, 15, 16 and so on. And this actually you can also, I don't know if this works now. Yeah, if you are pressing again F4, then you see that the dollar sign in front of the number and the letter vanishes, and again then both dollar signs vanish, and then you have another time F4, both dollar signs are again there, and this helps to be a bit faster than always clicking in the cell, clicking into the formula, typing in, and this is quite often takes very much time. So times, no, not times, this is A, so plus B, again fixing this number, times X. And these are then our numbers lying on our regression line. So and of course, these numbers we can also put into our diagram. Add data, X is the same, and here we have then for Y using these numbers, and then you see the orange data points are lying all on our regression line. Okay, so then what we have done here is, so to speak, taking all these squares. I have here the red one, so the next one would be then this little one here. And taking it down here. This one here, maybe another this one. This we can almost not see because this data point is almost on the regression line. maybe there, and the last one, oops, would be up here. So, and now if I would move this line a little bit to the right or the left, then of course all these areas, all these squares will change, and the sum of these squares will be then larger than the sum of these 6 squares which I have here. So the line is fitted into the data such that the total area of all 6 squares are minimized. And this is a concept which is behind the linear regression. Yeah, in order to sum up and to summarize, what do we have? We have then the slope, and this is the mostly the most interesting number, because this we can then interpret in an economic way. This means if I'm increasing x by 1 unit, then y is increased or falls by b units, if b is a positive or a negative number. Well, and this regression coefficient a, this is the cut of the x-axis, and so gives us the number for x is 0. Well, and as I already mentioned this in an economic way, this parameter a we quite often cannot reasonably interpret in an economic way. So if you think of our x is some input, then this would mean if I have no input anymore and this a is positive, that I still have revenue, still have cost, anything else. Sometimes it's possible, for example, for a classical cost function, then I can say this cut of the x-axis is just my fixed cost. Because, so quite often, a is not reasonably interpretable in an economic way. For example, if we think of x as an input, then a would be, for example, output, or if we think that of x as input and y as output, then a would be, for example, output for no input. And this is quite often the case, but there are some issues where you can interpret it, but there are issues where you can interpret a, for example, classical cost function. Well, and then for a cost function, quite often we make the ansatz C is some fixed cost, Z0, plus some marginal costs, Cx times x. Well, and then of course, C of x equals 0 is just C0, so this would be our fixed costs, and these are our variable costs. And then of course, B would be then our marginal costs. Okay. So in general, the linear regression measures the dependence between two variables, and then we have, of course, also a qualitatively manner in order to interpret this. And yeah, quite often we use this as an instrument of forecasting what will happen if I'm doing this or that. Okay, then of course I have to admit this is just a calculation, and give me some data, I always can do this calculation. So and then yeah, the people thought of, yeah, well, how reliable is my line which I'm fitting here? And this, of course, if we look at a diagram and my cloud of the points is very dispersing, then I would say, well, of course I can fit a line, but does it really does this line really give me a reasonable answer to my question? And for this, in the beginning of the 20th century, by Bravais and Pearson, they introduced the so-called correlation analysis. So the question is, how meaningful is our regression? And they introduced the so-called regression coefficient, which is then also called the Bravais-Pearson coefficient. And what is it? Well, for this, remember our introduction, and there we introduced the variance. This was the squared distance, sum of the squared distance, the n minus 1. I explained to you that this was the reason that it is an unbiased estimator. Well, and then I can introduce this concept also on the two-dimensional case, because this is nothing else than 1 over n minus 1 x minus x bar times x minus x bar. And what I'm just doing now is to write in here y minus y bar. And then, of course, I have somehow a measure of the dependence between these two variables. But of course, this measurement is now at this point hardly to interpret, because, well, if it's a high number, if it's a low number, how should I interpret it? I can always scale my data. If we go to economics, I can measure revenue in US dollar. I can measure revenue in what can we take in yen? I think there's a factor of 100 between. Well, if x and y are scaled by 100, then of course this number goes up or down. So how meaningful is this? And therefore, they normalized this number and the normalization is then just that we divide this by the variance of x and the variance of y, and in order to have the same units, we take not the variances, but here these are then the standard deviations of these two numbers. So normalizing the covariance by dividing the covariance with the standard deviations of x and y. Well, and this will then mean that this new number just lies in between -1 and 1. And then this correlation coefficient, or the squared of this correlation coefficient, has also a very nice interpretation, because it is directly related, and you see here y hat, to our regression line that you see here. This is the squared distance of the data points on the regression line minus the arithmetic mean, and this is the squared distance of the data points itself to the arithmetic mean of y. Well, and from this formula here, where is it? Here, we directly see as closer as our fitted points are, or as closer our actual data points are on the fitted line, then these two numbers will become closer and closer, and therefore if our regression coefficient is in the neighborhood of 1 or minus 1, then we are quite close with our data points on our regression line. Well, and then we qualitatively can interpret this. If our data points are quite close to the line, then maybe my model is quite reliable. And this means then, but here you have to be careful with the interpretation, but from a descriptive way, you more or less can say, well, I have an idea that maybe there is a quite good dependence when I have an R is in the neighborhood between 0.8 and 1. But you have to be careful that you do not mix up causalities with only correlation. You cannot say in this point of the analysis, well, I have an R of 0.95 and therefore my model is right. You are doing only descriptive analysis in this point. The only thing you can then say, well, maybe there is then something, causality between these two variables. And this we will then do later on, because then you have to make some assumptions about the errors and then doing the so-called inductive statistics that you then assuming, well, I'm assuming that really my dependence between marketing and profits has a linear dependence, and how statistically reliable is this assumption, and then you can formulate a hypothesis. I want to make only an error of 5% that I'm wrong. But still we are doing statistics, and still always you could be wrong. And this you have to be aware of. Okay. So, but we will do also our example. So let's be a bit faster. Yeah. What would you think in this case? In which neighborhood could be our R's when you see these diagrams? Some of you have already seen these numbers. So in this case, yeah, maybe this would be our regression line. So we would expect there some R in the neighborhood of 1. So maybe it could be something like 0.9. In this case, well, there is maybe somehow a falling dependence. So I'm coming from the left side. Maybe this would our regression line. And then I would have an R of maybe, let's say, minus 0.3. Here I see I'm lying just on the line. What kind of R would I then have? If I have, from a descriptive point of view, a full dependence, what would be our correlation coefficient? Yep. Yes, definitely. So here we will have 1, and here our data points are just distributed in a totally symmetric way. What would be here? Our R? Yep. Yes. Because there, what kind of line should I fit? Should I fit this line or should I fit this line? I don't know. Everything is as reasonable as the other one. Okay, then let's just calculate the numbers here. This is correlation. Oop. But I have this, I can't copy here, no. So it is X and Y, and I have 2, 3, 4, 5, 6, 7. And 8, 12, 15, 16, 21, 22. And the other one would be also, and it's 24, 9, 18. 29, 9, 18, 8, 19 and 8. 19 and 8. This was 24. And this was 18. Well, if I go to my formulas, then I know that it is, well, I can then go directly within these formulas here, or let's take B and the variances of X and variances of Y, because this I can directly calculate. So variance of X, variance of Y, and it doesn't matter which formula you need. So variance of X over variance of Y and squared root. So this is over Y. So root of var of X over var of Y. And then we need the slope. And this we already know how to get it with our formula Steigung and Y and the X values. And then we get R as B times this, and this we can also copy here. And here we have to be, yeah, we have already B, and so we obtain 0.985. How was my estimation? Well, this is then 0.985, and here we had minus 4.655, minus 0.465. 5. Oh, there we are. Okay. So, and now we want to come to the coefficient of determination, which has also, a very nice graphical interpretation. And this then, of course, lies only between 0 and 1. And the graphical interpretation is that r squared is just the, so to speak, relative area. And remember what I have shown you, all these little red squares, the distances between the actual data points and the regression line. And if we go to this formula here, then these are all squares with respect to the mean of our variable y. And this we see then here that we can say, well, this is our regression line. Up, where is it? Here. The dotted line is our y bar, and then every data point, and here up here is our data point. Then this is the square of this data point, which feeds into this sum here. And this area here, this area here, this is the sum. This is the area of the actual data point with respect now of our regression line. And on here, this is now the corresponding data point, which corresponds to this actual data point, but which is lying on the regression line. And still, this has also a distance to our arithmetic mean. And so we can say, since we are, so to speak, moving the horizontal line of the arithmetic mean just a little bit upwards, this moves our line a little bit more in the direction where our data points are lying. And therefore, through this movement, we can then, or we can interpret this as, well, now, since we moved this line, we interpret this as, now we explain a little bit where our data points are lying. And so this distance here, data points with respect to the arithmetic mean, is then our explained squared distance, where our actual data points are lying. This is, so to speak, the total dispersion, because this is, of course, nothing else than n times the variance of y, so the measurement of the dispersion of our data points. And with our linear regression, we, so to speak, then explain some part of the dispersion of our data points. And then we can say, if this r squared is, for example, 0.7, then we can interpret this that our linear model explains 70% of the dispersion of our data points. And this is a quite nice interpretation of this coefficient of determination. Yeah, and now we have 15 minutes left, and I think we will make it that we can also calculate then our r squared again for this now not with the formula of the variances, but with this formula in order to interpret this as the percentage of explanatory of explanation of our linear regression. So then let's copy also this one into our Excel file. Let's say this is 2 and this was 1. Yeah, this doesn't looks that nice. So here I have y hat, this is y hat minus y bar squared minus y bar squared, and this is y minus y bar squared, y minus y bar squared, and we can leave this, and this maybe a little bit smaller, 8. Yep. Yeah, again we need A and B in order to calculate y hat, the data points which are lying on our linear line. This we had already done. Let's do it again. Y and X. And this is the slope. Y and X. Then again y hat equals A fixed plus B fixed times X and y hat minus y bar, so we need y bar. This is then German Mittelwert of y, and y hat minus y bar 27, this again we have to fix, squared. There is something missing. This is the y and bracket. Oh, this was wrong. Here we are again. So equals, opening brackets, y hat minus y bar fixed, closing brackets, squared. Closing brackets, squared. Now hopefully it works. And y minus y bar equals y24 minus y bar fixed squared. And we need here the sums. So equal sum of these numbers. Oh, here I forgot to copy it. So the 572, this is our total dispersion. So this is the total variance, and here we have the dispersion now relative to our linear line, and this means then that this is our explained variance, and then we have r squared equals 482.7 over 572 is 0.84. And of course, for this we have also a formula, and since this is a coefficient of determination, the formula is Bestimmtheitsmaß, and feeding in the y values and the x values. And fortunately, we have here the same number. Question: if I would exchange in this formula x and y, what happens to the number? So if I take this formula here, putting this here, and now I exchange the b, the c with the b, and the b with the c. And if I now press enter, what do you think? If you are looking into your slides. What's about the internet? You have an idea if I now press enter? So the answer then, if I pose this question like this, do I get the same result or do I get another result? Oops. Well, if we look at the formula for our coefficient of correlation coefficient, or my coefficient of determination, which is just the square, if we look at this here, yep, not only maybe, it has to be the same, because covariance is symmetric if I take at first multiplier x minus x bar or y minus y bar. This doesn't matter because the multiplication is a so-called abelian group. Abel was a very famous Norwegian mathematician, and he said, when I have something where I can just interchange the direction, which one is first, then it's called an abelian group. Well, and of course, in the denominator, it's also doesn't matter if I'm calculating at first the variance of y or the variance of x. So then, if I push enter, of course, I have the same one. And I have 5 minutes left. Well, if I say then that here A prime and let's say B prime, if I'm interchanging here the variables, so at first x and second y, Well, then of course I have to have another number, because so if I say my model is a plus bx, and if I solve this for x, then of course I obtain x equals a minus a over b plus 1 over b times y. So, and this I then can interpret as an a prime, and this I can interpret as a b prime. And what one should also know is that calculating these numbers, also interchanging here x and y, that I could think that now b prime is just the inverse of b. If I calculate this, equals 1 over b, then I see this is not the same. And also I could think that maybe this would be just minus a over b is equal minus a over b and a minus sign. But also, oops, where did I do it? This minus is not right. This is not the case. But what I have is, now how does it was? Not b times b. No, it was this one. Is this times this. And do you see what this number is here? 0.84. Do you see this? Yep. Yeah, r, not r prime, but r squared, yeah. So this is b times b prime, and this equals r squared. Because sometimes one think, well, it doesn't matter if I'm fitting in a linear line within the data, it doesn't matter which one is on which axis. But when we have started linear regression, then we defined x as the independent variable and y as the dependent variable. And this you have also to keep in mind. You cannot, if you're doing linear regression, you cannot just interchange the dependent and independent variables. Then you get another, so to speak, best fitted line if you interchange these the direction of the dependence between the variables. Yeah, let's copy all this now in our slides, and then we are also done. And this was 0.4, and r is then the root of this in order to be complete, 0.92. So 0.84 and 0.92. Yeah. And with this, we are now ready. This is just then the interpretation we already did. If R squared is in the neighborhood of 0, then we have a very symmetrical dispersion of our data points. With an R squared in the neighborhood of 1, then we are quite close to the linear regression line. And the next time then we will go further because, of course, not only our marketing budget influences our profits, but also the people who are working within our company. Maybe the economic growth and the unemployment rate as a whole influences the profit of our little company, and so on and so on. And this is then done in the multiple linear regression, and most of your topics are about multiple linear regression. And then, yeah, we just expand our model that now we have not only one variable influencing, for example, our profit, our output Y, but we have many influencing variables. And this we will then do tomorrow. Thank you very much for today. Ja, auf den Aspekt hier, da bin ich gestolpert beim Kollegen. Das wird nämlich tatsächlich fast nie irgendwo gemacht. Und ich habe auch schon durchaus Leute gesehen, die dann gesagt haben, ja, ist ja egal, wie rum ich das ausrechne. Es ist aber eben gerade nicht egal. Muss mal gucken, vielleicht, wenn das nicht zu kompliziert ist, muss ich mir aber noch angucken, dann können wir das vielleicht auch in einer kleinen Übungsaufgabe zeigen, dass das eben so ist, dass eben die beiden Steigungsparameter gerade wieder die Korrelation ergeben.